Hi everybody and welcome to a new video in the audio processing for machine learning series. This time we'll look at the extraction pipelines that we need to extract both time domain features and frequency domain features. Before starting looking into this, I just want to remind you about the Sound of AI Slack community, which is a community with people interested in all things AI audio, AI music, and audio digital signal processing. So if you want to improve your skills and network with cool people, just consider signing up there. And I'll leave you a sign up link to the community in the description below. Now, let's go back to the cool stuff. In the previous video, we took a look at a few different types of audio features. So time domain features, which live in the time domain, frequency domain features, which live in the frequency domain, and finally time frequency domain features, which are features that provide us with information both about time and frequency. Now, we want to take a look at the extraction pipelines that we can use to extract time and frequency domain features. So let's start with time domain features first. Okay, so for the extraction pipeline, obviously the first step is just to look at an analog sound, right? So it could be the sound of a violin, a noise, and then once we get that sound, we want to convert that into something that makes sense and we can somehow like edit and manipulate with our computers. And for doing that, we need to go through the analog digital conversion process. In other words, we need to sample and quantize the analog sound so that we get a digital signal. Okay, so if you are not familiar with this process, I suggest you check out my previous video in this series that covers this like quite in detail. You should have it over here. Okay, so now once you have the digitalized version of the sounds, the next step that we want to do here is called framing. In other words, we want to bundle together a bunch of samples. And so here you see that, for example, frame 1 goes from sample number 1 to 128, frame 2 goes from sample 64 to 192, frame 3 from sample 128 to 256, and so on and so forth. Now, there's like an interesting thing here, which is that these frames are somehow overlapped, right? But I'm not gonna reveal you this secret right now. I'm not gonna explain why that's the case now. You'll notice by the end of this video, so stay tuned for that. Okay, so now let's understand a little bit better why we use framing before we extract features, acoustic features. Well, so we can think of frames as audio chunks that are perceivable, things that we can perceive. Now, the problem is that if we take a look at a sample, one single sample at a sampling rate of 44.1 kilohertz, which is the sampling rate for the CD-ROM, we find out that that sample has a duration of 0.0227 milliseconds, right? This is like very, very short amount of time. Now, if you're wondering how I got this number, well, that is just like the inverse of the sampling rate. So it's 1 divided by, in this case, 44,100, right? So now we know that like one sample is like very, very short, and we know that the duration of this single sample is way below the threshold of the time resolution for our hearing, human hearing, which is around 10 milliseconds, which basically means that all the things that are below 10 milliseconds, we cannot appreciate them as acoustic events. So with frames, what we want to do is to have enough time of enough duration of an audio signal so that we can appreciate that. And that makes sense from an acoustic perspective because it is like what we can hear, and the features that we want to extract are somehow related to what we can experience as human beings. Okay, so Now, another thing about frames is usually that they have a frame size, or in other words, they have a number of frames, which is usually a power of 2. Now, why is that the case? This sounds really weird, right? Well, that's because usually what we want to do when we move into like the frequency domain is just like apply the Fourier transform. And it turns out that when we apply the fast Fourier transform, which is a variant of the Fourier transform, having a number of samples that's a power of 2 is going to speed up the process a lot, right? So it's just like a matter of like speed here. Okay, so now typical values for the frames oscillates between 256 to 8192. Now let's take a look at the duration of a frame. And we have this formula down here. So we have the duration of a frame that's equal to the inverse, so of the sampling rate, so 1 divided by the sampling rate, and we have to multiply this by capital K, which is the frame size. And in other words, this first element here tells us the duration of a single sample, and then we multiply that by the total number of samples that we have in a frame. This way we get the whole duration of a frame. Okay, so now let's plug some usual numbers. So we can plug 44.1 kilohertz for the sampling rate, which is like a totally normal sampling rate. And then we plug in 412, which is a totally normal frame size at this sampling rate. And we get the duration of a frame to be around 11.6 milliseconds, which is just above the time resolution the human hearing time resolution, which is like around 10 milliseconds. Let's go back to the feature extraction pipeline for the time domain. Okay, so the last process that we saw here was framing. Now, once we've applied framing, the next step is just to compute the features, the time domain features on each of the different frames. But now what we want to do after that is to aggregate those results so that we get like a single kind of like feature, vector, whatever for the whole sound. So it's a descriptor for the whole duration of a sound, and we can aggregate that by using statistical means like the mean, the median, the sum, or things that are a little bit more sophisticated like Gaussian mixture models, for example, GMMs here. And so out of this process we get a final value. It could be like a value, so feature value, it could be a vector, so feature vector, or even a matrix, a feature matrix. And this basically is a snapshot for the whole duration of the audio signal that we are analyzing. Okay, so this is the feature, so the extraction pipeline for the for time domain features. Now let's move on to the frequency domain feature. As you'll see, many of the steps are basically the same as those that we found in the time domain feature extraction pipeline. So obviously we start from an analog sound, we do some ADC, so we apply sampling, we apply quantization, we get our digitalized version of the sound. So we have this audio signal, we frame the signal, and now we have a bunch of frames. Now, what's next? Well, what we want to do here is basically move from the time domain to the frequency domain. And we usually do that with a magic tool, which is the Fourier Transform. For now, yeah, I'm just like using this like magic wand, because for us, it's just like a black box for now. So it's some kind of like magic that happens, and we move from the time representation to the frequency representation, but we'll definitely cover like the Fourier transform more in detail in coming videos, so stay tuned for that. Okay, so just like a little refresher on time domain and frequency domain. So in time domain, we have the sound that's basically like visualized as the amplitude as a function of time. And so we see all the events across time for for the sound. Whereas when we move to the frequency domain, here we just look at all the frequency components of a sound, and we see how much they contribute to the overall sound. And indeed, on the x-axis, we have the frequency domain, the frequency or hertz, and on the y-axis, we have the magnitude, which tells us how much each of the different frequency bands contribute to the overall sound. Good. Okay. Now, so we would expect that's like the next natural step in the extraction pipeline would be to apply the Fourier transform, and that would be like just like natural, okay, so that we can move from time domain to frequency domain. But unfortunately, there's a major issue, which is called spectral leakage. Okay, so let's see what spectral leakage is and whether we can solve it. Okay, so spectral leakage happens when we are processing a signal. So when we are taking the Fourier transform of a signal that isn't an integer number of periods. And this basically happens all the time because like you have a certain amount of time worth of audio, and it's rarely the case that that amount of time has an integer number of periods. So what usually happens is that the endpoints of a signal are usually like discontinuous. In other words, these guys here are discontinuous because they're not an integer number of periods. And so what happens here is that if we have these discontinuities get translated into the spectrum or like the frequency domain as high frequency components. But these high frequency components really don't exist in the original signal. They're just some kind of artifact that appears because of the discontinuities at the endpoints of the signal that we are processing with the Fourier transform. So, in other words, what happens is that some of these discontinuities, frequencies at the discontinuities, are just like leak into other higher frequencies, hence the name spectral leakage. So now let's try to visualize this. So we are here in the time representation. We apply the Fourier transform and we get our spectrum or the frequency domain. And here we may have like higher frequencies which have like high contributions, right? And it's like here, like in this red box in the spectrum in this slide. Now, this is an example of spectral leakage. So these components, frequency components, don't really exist. They are just an artifact that comes from the discontinuities that we have in the original signal that we've analyzed. So when you have spectral leakage, usually you would get like some higher frequencies which have like some substantial contribution to the sound, and which indeed shouldn't be the case because these are artifacts. Okay, now is there a way we can resolve this issue? We can minimize spectral leakage. Well, luckily for us, there is one, and it's called windowing, right? Okay, so let's take a look at windowing. So the idea behind windowing is that we apply a windowing function to each frame before we feed the frames into the Fourier transform. And by doing so, we basically eliminate the samples which are at the endpoints of a frame. In other words, we completely remove the information from the endpoints. And what that does is it generates a periodic signal which minimizes spectral leakage, and we're happy for that. Okay, so a famous windowing function that you'll use probably 90–95% of the time when you do Fourier transforms is called the Han window. Here you have the this function here, and so K here, it just represents the sample. So this function is a function like of the Han window is a function of the samples. And as you can see here, we use like a cosine, and then we have visualization of the Han window for 50 samples. And as you can see here, it creates like this kind of like bell shape curve where the endpoints tend to be go to 0. Right. Okay, so now let's try to apply that to a signal. So we start with a signal, and so this is just like one frame containing 256 samples. Here we have the Han window, and now we can apply the Han window to the original signal so that we get a new signal that has been windowed, right? And this is the math that we run for obtaining applying the Han window to the original signal. In other words, what we do is we multiply the original signal by the Han window at each correspondent sample, right? And what we obtain is something that looks like this. And as you can see here, because we've applied the Han window, now we've completely smoothened the endpoints, right? And so we don't have those discontinuities anymore now, because the signal just goes naturally to 0 thanks to the windowing that we've used. Okay, but now we have another problem. We have another big problem. So now imagine we take a number of frames and we put them together. We just like glue them together. So here we have like 3 different frames that I've glued together. Now, as you can see, obviously what happens here is that at the endpoints of these frames, so at the beginning and at the end, we lose signal, right? And why do we lose signal? Well, because we just removed it through the application of a windowing function. Okay, and this is something that we don't want to do. We don't want to lose signal in when we do a Fourier transform. So how do we solve that? It seems like an impossible conundrum. Now, the solution is overlapping frames. And we'll see that in a second so that we can solve the initial mystery of overlapping frames that I mentioned at the beginning of this video. But before we get there, let's just like take a look at normal non-overlapping frames. So what we would usually do like with non-overlapping frames is that we just like choose a frame size and we apply that to a signal. And so this is like, for example, this vertical red bar represents like the first frame for this signal. Then we move on to the second, the third, fourth, fifth, and sixth frames. And as you can see, we don't have any overlaps here. But if we were to do this after windowing, we would lose signal. So how do we solve that? With overlapping frames. And so let's visualize overlapping frames. So we start with the first frame here, and then we have the second frame. And as you can see, there's a part there that overlaps. And yeah, this is like the way we overlap frames. And by doing so, what it means is that we kind of like account for the information that we lose at the endpoints because we are overlapping frames. Okay, and so we can continue to and have a third frame over here, a fourth, and a fifth. Basically, you get the idea. So we just like overlap these frames every time. Okay, so now let's take a look at a couple of important concepts. So we already saw like the frame size, which is get this basically, and it's like the number of frames that we consider, the number of samples that we consider for each frame. And then we have another very important concept, which is called the hop length. Sometimes you'll hear this concept referred to as hop size. So the hop length is basically tells us the amount of samples that we shift to the right every time we take a new sample. Okay, now let's move on, because now we are at a point in our feature extraction pipeline for frequency domain features where we can apply the Fourier transform. So indeed, after windowing, we apply the Fourier transform and we get a spectrum, hopefully with minimized spectral leakage. And then after that, we just go back to like the same steps that we used for the time domain feature extraction pipeline. So we compute frequency domain features on each frame, then we aggregate these results for the entirety of the audio signal using some statistical means, and finally we would get a frequency feature, frequency domain feature, value, vector, or matrix. Okay, good. So now you have a clear idea of the pipelines that we should use when we are dealing with time domain features and frequency domain features so that we can extract them. So what's next? Well, it's time to start digging into time domain features. So next time we'll start looking into time domain features, a bunch of these, and understand what they are and how we can use them for different applications in machine learning. So stay tuned for that. So that's it for today. I hope you've enjoyed this video. If that's the case, please remember to leave a like. If you have any questions, as usual, leave them in the comment section below. I'll try to answer those. And I guess that's all for today, and I'll see you next time. Cheers.